So if we want to calculate the molecular speed in an ideal gas, so like the speed of a nitrogen molecule moving through the air, excuse me, we can go back to the equation we derived on the last page, or last screen, last video, and say, look, the kinetic energy of a single molecule is just 3/2 kT. That's just for one molecule. The total kinetic energy was that multiplied by n, and the way we derived that was by writing 1/2 the mass times the mean square of the velocity is equal to 3/2 kT. And so you can solve this for v squared average. There's a subtlety here that I'm going to kind of just not talk about too much. It's equal to 3 kT over m, because I cancel the 2's in the denominator on both sides. And then I can say the square root of that, which we call VRMS, is equal to the square root of 3 kT divided by the mass. And so the speed of a molecule is 3 times the Boltzmann constant times its temperature in Kelvin divided by the mass of a molecule. And we call this the RMS, which stands for the square root, the root of the mean square. And so there's a subtlety here. This is what we used here was actually the average square velocity instead of the average of the velocity squared. And it makes a subtle difference, but we'll just be kind of referring to it casually as the average velocity or the RMS velocity. And so first we have to calculate that m. So if we want to do this for nitrogen, right, the nitrogen molecule, then the mass of a single molecule is the molar mass divided by Avogadro's number. And so that's the molar mass of nitrogen is 2 times 14, I should say, 2 times 0.014 kilograms, because that's the mass, that's the atomic weight. 14 is the atomic weight, and a mole of them is 14 grams, which is 0.014 kilograms. And I could say per mole divided by 6.02 times 10 to the 23rd per mole. And so that gives us 4.65 times 10 to the minus 26 kilograms. And so now, so that's the m. It's just the mass of a single one. It's just it's the mass of a mole of them divided by how many are in a mole. So it's mass per mole divided by molecules per mole, and that gives you 4.65 times 10 to the minus 26. And so now VRMS is the square root of 3 times the Boltzmann constant, which is 1.38 times 10 to the minus 23rd joules per Kelvin. And we're going to say at room temperature, so at 293 Kelvin, say, times 293 Kelvin. So that takes care of the 3, the K, and the T. And I'm going to divide that by the mass by 4.65 times 10 to the minus 26 kilograms. And what I get for that is about 511 meters per second. That's actually faster than the speed of sound. The speed of sound is 344 meters per second. So we're getting peppered by all these tiny little molecules going around at high speed that when you take them in groups, they sort of act like a pressure. Instead of feeling individual collisions, we sort of feel the collective action of all of the molecules pushing on us in an average sort of way. So let's talk about the mean free path. That's how far on average a molecule goes before it collides with another molecule. And so I'm going to draw some molecules in here, and I'm going to try to draw them as spheres, because we're just going to make an approximation that they're spheres. Right? And so we're going to say, look, the density, the number per volume, the number density, is just the total number in the box divided by the total volume of the box. Right? however big my container is. And so now let's look at this guy. Each of these molecules has, say, a radius r. Right? So as it's traveling through the gas, it's going to occasionally bump into another one. And we will know the average time it takes to hit one molecule. To hit it, on average, how far does it go before it hits a single molecule? And so the way we're going to do that is we're going to say, look, in order for it to hit another molecule, the molecule, since they each have radius r, their centers have to be a distance 2r apart, right? If I draw another little molecule here, right? If their centers are 2r apart or less, then they collide. And so what I'm going to do is draw a little circle around this guy. So here's the molecule that I'm talking about. And I'm going to draw a little cylinder. I know this is going to look a little weird for a second, right? But I'm trying to draw, so you're seeing a round molecule and then the edge of a cylinder, right? And so that's the back edge of a cylinder. And say this is the front edge of the cylinder. So this is the side of the cylinder, sorry. And so this is the path the molecule is going. Its velocity is this way. And we're going to say, look, this distance is the mean free path. When the number of molecules per unit volume in this cylinder that this thing sweeps out is 1, right? When the number of molecules inside the volume that's swept out by the cylinder is 1, then this is the mean free. Then that's the correct mean free path. And so, if this says area A, and this is length lambda, then lambda times the area is equal to the volume of the cylinder, right? Not the volume of the container, but the volume of the cylinder. And so when N over V times the volume of the cylinder is equal to 1, then that means there was 1 molecule in that collision, and my lambda is going to be my mean free path. And so if I write this out, I can say, look, N over V, that is the number of molecules in gas divided by the volume of the gas, times lambda times A is equal to 1, or lambda is equal to V over N times A, which is V over N times the area of this thing is pi times 2r squared, or V over 4 pi r squared N, where r is the radius of the molecule. It turns out that there's a subtlety here that has to do with these root mean squares we were talking about before, and this is not quite right. The actual value of lambda is off by a factor of the square root of 2, and so I'll say correct. And I'm just stating this. This is just a description we gave. I'm stating this is V over 4 times the square root of 2 pi r squared N. Okay, and so this is actually this is the thing I'll be calling lambda here for a second, right? And so I'm gonna clear this out a little bit, and I'm gonna say, look, we can use the ideal gas law, right? We can say PV equals NKT, and so V over N is equal to KT over P. You follow that? And so I'm going to replace this V over N with KT over P, and I get lambda. Now that's this lambda. I'll stop writing correct next to it. Is equal to KT over 4 times the square root of 2 pi r squared times the pressure. And notice here, when we talked about V and N, if we wanted to solve this problem, well, we'd have to pick a cubic meter and how many molecules there were in it. But here, I've by using the ideal gas law, I can say, well, what's the temperature? What's the pressure? Is it atmospheric pressure? Is it room temperature? And I can just calculate this thing now. And so let me just write this one down here for a second, and we'll do a simple calculation here. So we can use this this equation, which is the mean free path is equal to kt over 4 times the square root of 2 pi r squared times the pressure, to calculate the mean free path of a nitrogen molecule at room temperature at atmospheric pressure, right? And the only thing we have to find is we can just look up the radius of a nitrogen molecule, which is roughly that. And so we can just evaluate this now, right? This is 1.38 times 10 to the minus 23 joules per Kelvin times 293 Kelvin divided by 4 times the square root of 2 pi times 1.55 times 10 to the minus 10 meters squared times 1.01 01 times 10 to the 5th pascals, right? And so what I get for that I get about 9.4 times 10 to the minus 8th meters, or maybe roughly 10 to the minus 9 meters. And so roughly 10 radii, excuse me, roughly speaking, which is about what we said earlier when we were talking about the relative densities being off by a factor of 1,000, so the spacing is about a factor of 10. And so roughly speaking, that's what we see. And so that's the mean free path for nitrogen molecules moving around in air. So if you want to evaluate the average time between collisions, right, instead of the distance, the mean time between collisions, we use the variable tau for that. And what that is it's equal to the mean free path divided by the average velocity, the RMS velocity, right? And so for that, we got, this comes out to, if you remember what the mean free path was, it was kt over 4 times the square root of 2 pi r squared times the pressure, and now all we need to do is put a VRMS there. And if you wanted to be a little more thorough about that, you could write that this way. You could say, well, that's kt over 4 times the square root of 2 pi r squared times the pressure, and if you remember, the RMS velocity was the square root of 3 kt over the mass, right? And so I could rewrite this way. I could say it's the square root of mkt, right? Because the kt, square root of kt in the denominator and the kt in the numerator gives you a square root of kt in the numerator. The m goes up into the numerator. I can combine the square root of 3 with the square root of 2, and I can say 4 times the square root of 6 pi r squared times the pressure, and that's the mean time between collisions. And if we wanted to do nitrogen, we've already done that, because we can already say that for nitrogen, the mean free path was about 9 times 10 to the minus 8 meters divided by the the velocity of the nitrogen molecule, which is at about 550 meters per second. So in round numbers, I think I used 9.4 for this guy here. I did. Okay. Let's try this one more time. 9.7 times 10 to the minus 8 seconds. Anyway, a small time between collisions.